Hello, this is Dr. Viv. Let's start out by talking about the general properties of potential energy curves. For simplicity of discussion, I will take the potential to depend on only one variable, which is x. The force f of x is given by the negative derivative of the potential. Now what this corresponds to in terms of graphical features is that du by dx is the slope of the graph. So if I take any point, such as this point, then the slope of the graph is a tangent I draw there. And the tangent here is positive, but because of the negative sign, the force is negative. Force being negative means that the force is in this direction, to the left. That kind of makes sense because if I place a small mass like a marble and think of this as a molded plastic tray, and I place a marble there, the marble will tend to roll to the left. So that's the picture I would like you to have in mind. Place a little bead or a marble. You can think of this as a wire and with a bead on it, or you can think of a marble going on a hill. Take another spot here. The slope as such is negative for this point. However, because of the negative sign, the force is positive. And sure enough, if you keep a bead, then it goes in this direction, or the positive x direction. So that's the relationship between the force and the potential energy. Now, special care should be taken at places where this is equal to 0. If that's equal to 0, then no net force acts. Such places are known as equilibrium points because at those places the total force acting on the particle is 0. Special points are places like this. So look out for places with flat tangents. Now, even among flat tangents, let's call these points of equilibrium x sub e. So there are 3 equilibrium points in this particular potential energy curve. Even at those points, there's some difference between these two and that. If you place a marble here, it's very easy to dislodge it and make it go this way or that way. Such a spot is known as an unstable equilibrium. Spots like these are known as stable because if you dislodge a marble either to the left or to the right, it'll keep coming back and oscillating back and forth about these equilibria. So the calculus criterion is related to concavity of the graph. These two are concave up and that's concave down. So at xc, if we have the second derivative, d2u over dx squared is bigger than 0, or concave up, then we are led to an unstable equilibrium. Actually, wait, that's stable equilibrium. And if the second derivative d2u over dx squared is less than 0, which is concave down, then you're led to unstable equilibrium. Having a picture like this in mind is better than thinking in terms of calculus, but if you have to write it in terms of calculus, then this is how you would write it. So one other feature of these curves is in one shot, they also give you the nature of motion. Let's study that. Suppose I have the total energy of the system to be E naught. Then the system's total energy will be comprised of the kinetic energy and the potential energy. Now, because the total energy is fixed, the potential energy is given by this curve. It means the kinetic energy is the balance. Whatever is left over from E to the potential energy is the kinetic energy. So that's going to be kinetic energy. As you can see, this E naught curve at this point and at this point, the kinetic energy is exactly 0. And at this point, the kinetic energy is maximum. So that makes sense. When the potential energy is minimum, the kinetic energy has to be maximum so that the sum of the kinetic and potential will be constant. Also observe that once you get to this point, you cannot really cross the barrier. That energy barrier prevents it from going there. But let's suppose the particle was here initially, then it would be trapped entirely in this valley and has no possibility of getting into that valley. But suppose you had an energy E1 that's bigger than E0, then you can clearly see this particle will have enough energy even here, because there's a kinetic energy left over even at the topmost point, so it will roll over up to there. So it can go all the way, and I don't know what's going on here. This is how we study the motion, by just looking at the energy diagram. So this has all been very general. So let's take a specific example to put some teeth to the discussion. All right, here's an example. Let's take a simple potential. U of x equals 2x squared minus 3x to the 4. So I think it might be easy for me to plot this. Let me try doing that. Because I've plotted the I have to look at both positive and negative values. X squared is like a parabola, and for small values of x, that will dominate. For large values of x, x to the power 4 will dominate, and that's going to have a negative sign. So at some point I can expect this graph to turn around and get dominated by x to the 4. So that's how the graph should look. It should be symmetric on both sides, because changing x to minus x does not change the nature of the graph. So all that I can just get by looking at the function. Now let us find out where these intersections occur. So the intersection will occur when u is equal to 0, and that's given by x squared times 2 minus 3x squared. So the potential is equal to 0 at x equals 0. There's a double root there, which means that it's going to be concave up like that. And then when 3x squared is equal to 2, which means that x equals plus or minus 2/3. Let me mark those points. Root 2/3. Now we have to also figure out what the special equilibrium points are. There are going to be 2 unstable equilibria and 1 stable, just by looking at the figure. Let's see if calculus gives us the same insights. So to calculate the equilibrium points, you just have to take the derivative, because the force is the negative derivative of the potential. So I'll take negative f, which is du by dx. And that's going to be 4x minus 12x cubed. And I have to set this equal to 0 to find equilibria. Plural, because I expect to find 3. So I'm going to get 4x is common. So I get 1 minus 3x squared is equal to 0. So the solutions to this are xe1 is equal to 0. That comes from setting 4x equal to 0. And then if I set 1 minus 3x squared equal to 0, I'm going to get xe2 equals plus 1 over root 3, and xe3 equals negative 1 over root 3. So those are my 3 equilibria points. There's no difficulty in identifying them in this diagram. All right, and then of course 0. So we have identified the stable and unstable equilibria in this problem. Just to verify that this matches the concavity criterion, I'll take the second derivative. the second derivative u double prime, that's just d2u by dx squared. I'm using the prime notation. That would be called u prime. So u double prime, if I take the second derivative, I'm going to get 4 minus 12, well actually 12 times 3, or 36 x squared. All I have to do is evaluate it at each equilibrium point. So at xe1, u double prime at 0 would be equal to 4 minus 36 times 0, which is 0, or 4, which is bigger than 0. So indeed, that is the stable equilibrium point. That was obvious by just drawing the picture. And at xe2 and e3, you're going to get the same type of equilibrium, because plus or minus really doesn't matter when you insert it into the square term. So I'll just work out at both of them at once. Plus or minus 1 over root 3. What does that give us? It's 4 minus 36 times. When I square the square root, I just get 1/3. So that's 4 minus 12, which is negative 8, and that's less than 0. So sure enough, that is unstable. Now, we can also find, just again to continue the fun, and because I have some extra time left, I usually try to keep these videos under 15 minutes. So let's also find the critical value of E naught, or E naught critical, so that the motion stays entirely in the stable region. If it goes beyond that, the particle is lost forever, because it's going to slip off to either minus infinity or positive infinity. If you want it to remain trapped between negative 1 over root 3 and positive 1 over root 3, you need to have an energy that's no bigger than that. So let's find out the critical energy for stable oscillations. Well, all we have to do is calculate the potential at plus or minus 1 over 3. So the potential function is right there. Let's do it. U at plus or minus 1 over 3 will turn out to be the stable energy, E naught, critical, and that's 2 times x squared, which is 1/3, minus 3 times x to the 4, which is the square of that, or 1/9. So I'm going to get 2/3 minus 1/3, which is 1/3. So that's the critical energy, whatever unit system we are in. It should not exceed 1/3. The total energy of the particle should not exceed 1/3 for it to be stable.